So thanks for having me. All right, so yeah, that's the case. So we have this. We have the multi-electron, and then we have more though, right? What's the other additional ones that we have for atomic orbital energy level diagram? They call this orbital energy level diagram, but that doesn't differentiate between atomic and molecular. We have molecular orbital energy level diagrams as well. And so if we look at a MO, which we call molecular orbital, there's more that you have to memorize. Fortunately, you don't have to memorize these just yet. But these are molecular orbital energy level diagrams. These are in chapter 11, so it's not quite yet. But what people do is they memorize this. They memorize sigma 2s, sigma star 2s, sigma 2pz, pi 2px, pi 2py, and they have different shapes to them. And a lot of those shapes are not so difficult to remember. But
what does the star represent between sigma 2s and sigma?
The star represents what we call anti-bonding. These are anti-bonding orbitals. These are bonding orbitals, but we haven't gotten there yet. So you don't have to worry about this. But before we get there, we don't want to get all these orbital diagrams mixed up. So we want to make sure that we understand the atomic orbital energy level diagrams, and that first before we move on to these orbital energy level diagrams here. And these can get quite complex. These are the simple ones. These are for the diatomics. And then we can get to these. These are molecular orbital diagrams here. They get a bit more complex when we look at different factors in there. This one's for transition metals. Yeah.
Do they have orbital diagrams of organic compounds?
Yeah, we have molecular orbital diagrams. You want to see?
I'm curious what the organic compound.
Which one would you like to see? Unfortunately, we don't have Spartan on this computer. MO diagram for, you want ethanol?
Yeah. Yes.
Let's try ethanol. These are some, I don't know if this is ethanol here, but these are molecular orbital diagrams for organics. Specifically for ethanol. There are a whole bunch. Here's one of them. You know, so we have the positive amplitude, the negative amplitude, wave function for the whole molecule. This is a full quantum mechanical approach. Full quantum mechanical approach is much more difficult than what?
The classical approach.
Well, we're doing quantum mechanical approach. There are two levels of quantum mechanics that we approach. Kinda. Not atom by atom, but it is atom by atom, but what specifically about each atom? Like, here, high quality images of ethanol. Here's some. They call this the HOMO, the HOMO, and they call this the LUMO, the LUMO. These are the two most important molecular orbitals that we often look at, the HOMO and the LUMO. This is a HOMO animated GIF here, but and then we have the LUMO. And so it just goes on. So before we go on to more complex stuff, we want to make sure we understand the simpler stuff. And that is, we want to know all the atomic orbitals. Is that it for all the atomic orbitals? No. What else do we have for atomic orbitals? We have the hybridized atomic orbitals. And so this is why I wanted you to draw the energy level diagram, the whole, including the core electrons too. And so you should be able to draw the energy level diagram for SP, SP2, and SP3 hybridized atomic orbitals. That's going to look a little different than this. Here. It's going to look a little different. It depends if it's third period or... Actually, this is screwed up too. What's wrong with this diagram?
It should be 1s, 2s, 2p, 3s, 3p, 4s.
Right, the 4s is missing. This is not divided into periods or shells, so this is not great either. What's a good diagram? This is, this is a problem, unfortunately. That diagram doesn't look so great. We have a better one. And so let's take a look for a better one. There's different ways. People like circles. If you like circles, you could draw like this. This one's correct because we see the 4s in the green here, and then the 3D in the yellow, and then the 4P. That one looks good. Or if you prefer boxes, then we could see the 4s, 3D, 4P clearly here. Or if you like lines, this would be 4s, 3D, 4P. I don't know why our book doesn't do that. But it's all right.
You should email it.
Yeah, should. Should email them, but it's all right.
Put out a small edition. Professor Ray, use text seconds.
Because it just ends up, the students will memorize that figure and then draw it and then get it wrong, unfortunately. But there are plenty of figures that are correct. So you should be able to draw that, and then you should be able to draw the orbitals, SP orbitals, and the SP2 and the SP3.
SP2. Or say SP1. It would fall. Say it was 2 SP1.
Mm-hmm.
Would it fall in between 2S and 2P?
Yes. It'd fall like 50-50 between the two. The average is, you take the average energy, the weighted average energy, depending on how much P. The more P you have, the closer the P gets.
Yeah.
The more S you have. And so if we look at the original orbitals here, the S and the P's here, and we're looking at SP, SP would be straight in the middle because it's 50% S, 50% P. So those orbitals would be, SP, here. That would be the hybrid. It would be right in the middle. If it's SP2, it's going to be closer to P than S, and SP3 will be up here, 2/3 or whatever, 3/4 of the way. 3 parts P, 1 part S. Yeah. So could you draw the energy level diagram and then sketch the orbitals? Then you're good. That's it. You don't have to do all the all that overlap stuff. All that overlap stuff is what? Was called what? Valence bond theory. The easiest thing when it comes to studying for tests is not to wait, right before the exam, the night, because it becomes overwhelming. But if you like reviewed yesterday's notes, let's say you took some notes and you reviewed, valence bond versus, no, ionic, valence bond versus,
LCAO.
LCAO is a part of it, but we don't call it LCAO, we call it, no, we don't call it that. Valence bond theory versus molecular orbital theory. You know, it's much easier rather than the night before the test to review that, to review it as we go on. Fortunately, valence bond theory and MO theory are not going to be on this test, right? But they're going to be on the next test. And they're going to be on the next test. You want to know some stuff.
We're gonna learn more about that, right? Like.
Oh yeah.
Molecular orbital theory.
We're going to learn a lot more about molecular orbital theory because we're going to have to look at the MO diagrams here. We're going to be able to sketch some simple molecular orbitals. Some of these complex molecular orbitals would be a pain to sketch.
May I request an MO diagram?
Oh, for what?
Glycol.
Glycol. Actually, we had the software, but they didn't want to purchase this again. That you could generate your own MO diagram. And so I don't know if I have the MO diagram for glycol. It doesn't look like I have it yet, but it's there. All these MO diagrams we can, we don't do by hand. We just use a computer to generate these.
I imagine that to be a lot faster than doing it by hand.
Yeah. Well, it is going to be a lot faster than doing it by hand. Whereas a valence bond is easy to do by hand and do that. So as far as hybrid orbitals go, just note that there's more atomic orbital energy level diagram that we have. So if this is second period, then we'd have the 1s orbital here. And then we'd still have the 2p orbitals here. They're unhybridized, and then we have these. Number 28?
Yeah.
Which, the homework or?
Exam 3.
Exam 3. All right, the red line in the hydrogen atom spectrum is related to which electronic transition. So there are two things for this one that you could answer. One is you could just figure it out by calculation, or two, you could have had it memorized. So for example, the hydrogen atom we're just looking at, and we could use the Bohr or quantum mechanics. Bohr and quantum mechanics gives the exact same equation for energy. For a single electron species, the energy only depends on n here. When we have the n final is 1, so let's say we're looking at the 2 to 1 transition, the 3 to 1 transition, the 4 to 1 transition. Those are fairly high energy transitions, and those, by memorization, turn out to be UV, ultraviolet light. And so for the hydrogen atom, the ultraviolet is not visible. And so we look at the emission series, yeah. So I told you there are more series than what's given in the book. The Lyman, it's named after Lyman because Lyman discovered these lines in the UV. The lines in the UV correspond to these energies, which corresponds to the wavelength. And these are short wavelength lines, higher energy. So Lyman discovered these using a UV detector, that can detect UV photons. Balmer discovered these, but these, anybody could have discovered these because they're just based on visual detection using your eyes. Bashan discovered these ones here.
Those visible or
No, these are infrared, and so these are invisible also. Then we have the bracket, which are going to be infrared and fun.
that be microwave?
It depends on where it goes. No, there's
Still infrared?
it's still infrared. Yeah. It could potentially emit microwaves. Usually with microwaves, those are very small. And so you see there's a whole bunch of little lines in there, along with the big ones.
Effective noise.
But we don't need to know these series. What you need to know is for the visible light, it doesn't go all the way to the first floor. It stops at the second floor. And so red is going to be the lowest energy visible light, so it's got to be a 3 to 2 transition. And so that's the way you could have done it. You would have had to know that for visible light, we end up the second floor. Eventually we'll go down to the first floor, but if it goes down to the first floor from the second floor, it's a UV. Anyway, and the lowest energy of the visible will be 3 to 2. Okay, that's number one. Number two is you could do the calculations. I don't know if you want to do this and how much time you have. The other option is you calculate the wavelengths for all of these. So here you might start off with the lowest energy and then the highest energy. All of these are ending at 2. And so we can start off with the lowest energy and see if that's in the infrared or the visible. And then maybe go to the highest energy. And so what we need is we need the Rydberg equation for this. The Rydberg equation you don't have to memorize. It would be given minus R sub H 1 over N final squared minus 1 over N initial squared. And so R sub H would be given, and so we just plug in 1 over N final squared. And so 1 over N final squared would be
It's ending at 2, so it's not
4 minus 1 over initial squared.
Let's start with the lowest one, so
9. Then we can calculate the energy of this photon here. Calculate. And then once you calculate the energy of the photon, then this is equal to hc over lambda. And then lambda is equal to this hc over the energy of the photon. And then that comes out to about 750 something nanometers, which should be in the red. We did that. Okay, is that okay for number 28? So these are it. This is the red, this is the green, this is the blue, this is the violet, and then 7 to 2 would be ultraviolet.
wouldn't that still be violet?
It could be. I mean, if they're showing 5 lines.
No, 62 is 72. So it's like, oh, it's just 2 to 1. That's like 2. Yeah.
So this is it with the red, the green, the blue, the violet, and the ultraviolet. And this one for the Balmer series. You don't have to know the names of the series. Okay, other questions?
Could you do 73 and 74 on the chapter 8 homework?
Well, A contour map for an atomic orbital of hydrogen is shown at the top of page 370 for the x, y, and xz planes. Identify the orbital. So let's look at the first orbital here. What does it kind of resemble?
A clover.
A clover, four-leaf clover. So we suspect it's a d orbital, number one, because it's a clover. Okay, number two, what n? The n that we can determine is going to be based on how many nodes we see. That slices up the orbital. And so how many nodes do you count there?
It's 3, 2.
Well, I see these. These are spherical nodes.
Yeah.
So 1, 2, but I see more.
And then the cross sections.
Yeah, then there's going to be a planar node here, 3, and 4. A planar node here, 4 nodes. If there are 4 nodes, what n? It's got to be. This is going to be a 5d orbital. 5d orbital. So when I look at this orbital, it looks like a, yeah, which is a, what type of orbital? P. So this is a p orbital, but I just got to figure out what n that is.
And it's 3 nodes.
Yeah. So there are 3 nodes, 1 planar and 2 spherical, which means it's going to be 4p. It's a 4p orbital. And it's going to be a 4p x, because they put the x vertically. This one is going to be an xy plane, so we call this a 5d xy, because it's in the xy plane. Now, if the lobes match the axes, then we call them x squared minus y squared. That is, if we rotate the axis here so that the x-axis lines up with the lobes and the y-axis, then it's, again, x squared minus y squared. But if the lobes are in between the axes in the xy plane, we just call it xy.
Are they like the same orbital though? That's what the answer is saying, it's just rotated.
Okay. Well, if that's the case, if this is just rotated, then they're the same. So we aren't seeing the other node here, and we aren't seeing the other lobe. And so, yeah, if this were just a side profile view, then it's the same. I didn't notice that. I thought they were different orbitals. But you can't tell by one drawing. I mean, if we were only given this drawing, then couldn't tell it's a G. And so, okay, that's fine. This is side profile. This is all we need. And so if this were P, then that would have been it.
And so it's because on the first one, that plane is the XY plane. And then
If you want to get fancy with the names,
well, is that the reason why they're the same? Is that's how you can tell that it's rotated? Because of what axis it's showing?
I couldn't tell it's rotated because, oh, I see. This line is the XY plane. I didn't see, this is the Z. So we're looking at the XY plane here. But if we, if the Y, then where's the Y? So if this is the X, the Y is sticking out. If the Y is sticking out and we rotate it this way, then that makes sense. Yeah, this would be rotated here.
And not in the second one, the Z sticking out?
Yeah, and the second one, the Z's got to be sticking out. So, but if we rotate it this way, they must have rotated it a different way then. They grabbed it by which axis? This is very odd.
I guess they would grab
Because
it by,
normally I would think they just grab it by the Z axis and then rotate it 90 degrees.
I thought they grabbed it by the x-axis, which is our profile.
But if they grab it by the X axis, then that's the wrong drawing. They could have grabbed it by the Y axis, but it's still, if they grab it by the Y axis, which is here, and then rotate it, no, we aren't going to get that drawing. They'd have to grab it by the X axis, unless this is the Y axis. But anyway, this is a very weird rotation. Normally, well, in chemistry, what we do is we grab it by one axis, and then we do different rotations. Like the twofold rotation means two turns until you go back to threefold rotation will be three, not turns, but three partial turns to go back to origin. A threefold axis would be 120, 120, 120. That would be it. And so in chemistry, we do a lot of rotations. So here, if this is this orbital, then there's something funny about this orbital. One thing that's funny is this. If I rotate it along the x-axis here, what happened to these two? Because I see the inner ones there, but I don't see these ones here.
They get hidden.
They aren't hidden because if I rotate it along the x 90, then these come out in the front. So that's on the z-axis. So they're rotating on, they're tilting this up like this. So they tilt this up like this, and then that's going to bring this pancake up, but the edge of the pancake's missing. Do you see that? So these two, when I look at these two look like separate diagrams to me. They don't look like the same. Can you see that?
Yeah.
So there's a problem with this. They either cut away these two lobes here, or they're not showing these two lobes in the back.
Yeah,
But even if they cut away these two lobes, there's not enough gap here to see these.
yeah, I was about to say, I think they basically, brought the profile Z up and then just opened it up. Like it's
They just,
cracked.
like,
I don't know why they did that.
in the front.
They didn't have to do that. They could have just done a standard rotation. If you do this on a computer, you just do a standard rotation, you just see it. It's very simple. This is why this threw me off, because these are weird looking diagrams. There's something missing here. You know, when we look at it on the profile here, you can't see all the way to the edge of the spherical node here. You know, like you can here. Why are we seeing this? It doesn't make sense. These has got to be blocked by these lobes here. It doesn't make sense. So that's why automatically I didn't think they were the same. I thought they were different because the rotations wouldn't yield that. Because you spend a lot of time on the computer rotating things, you'll see these. But anyway, that's all right. We'll just ignore the second one and just look at the first one. Looking at the first one, what kind of orbital is that?
That is a
F. Yeah, that's got to be an F.
that looks like a hexagon.
Maybe it's a G, who knows? But yeah, it's got to be an F, right?
No, it's got 10.
I'm sorry?
It's got 10. So I think that's
10.
12. That's 12.
So anyway, identify the S type, S, T, D, F, G. So this is going to be an F. And then how many nodes?
3, 2 planar, 1 step.
2 planar or 3 planar? 3 planar and spherical. 5F. Yeah. 5F. Is there such thing as a 5G? Does a 5G orbital exist? Well, F is what, 2? Is that right? Or 3? And L. No, I mean, there are different ways we can figure it out. But one way is S is 0, P is 1, D is 2, F is 3, G is 4. There is a 5G orbital that exists. Yeah, 4F is the first F, and then 5 would be the 5 would be the first G. But we know what F orbitals look like. They had a figure in the book, or we could just go online and look at F orbitals. When you do homework, all resources are available, not just the book, but anything is available. And these are the F orbitals here. So 1, 2, 3, 4, 5, 6. Six lobes. 6 lobes on an F. And then it's going to be diced into smaller pieces. But when we look at this, 1, 2, 3, 4, 5, 6 major lobes. So this has got to be an F. It's not a G. What does a G orbital look like? Let's find out if there's a pattern. You might predict 8 lobes.
Maybe no.
We'll just look at the main, 1, 2, 3, 4, 5, 6, 7, 8. 8 lobes. You got it. So maybe there's a pattern there. And so we'd look. And so these are the G orbitals, right? Let's test our pattern here with H orbitals. How many lobes do you predict on an H orbital? Main lobes?
10. Like 10?
Yeah, maybe 10. Let's see if we can find the H orbitals here. H orbitals. Yeah, here, 6H. Let's count it here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Pretty good. I think, But it's complicated because they're going to be diced in certain ways. So what I'm looking at is just the main, because if you look at this is a funny one with a hula hoop type deal. But if you look at this one, then yeah, this is okay, 10. But when you look at this one, then it's weird because we got conical. You see conical?
Yeah.
Nodes and other things that kind of dice things up differently. Oh, this is pretty cool. You can see the nodal, nodal plane, nodal spheres. And this one's weird, etc. Okay, did that answer the question then? Yeah. Were there other questions? No. All right, in chapter 8, what are these diagrams called? Yeah, orbital box diagram. This one has a noble gas abbreviation, so neon, 1s2, 2s2, 2d6, and then the bands here. So the neon core, we call it. Neon core. This would be third shell, valence, third shell elements. Yeah. We could do the same thing with hybrid orbitals. We could make an orbital box diagram for hybrid orbitals, but we typically don't. Well, actually, we do too. You can do the exact same thing, orbital box diagram with hybrid orbitals. I didn't, but it's possible.
It's basically what we were doing with the energy level diagram.
Yeah, exactly. The energy, you just copy down the energy level diagram. This flat. And then you guys know about the periodic table, right? In quantum. The periodic table is based on quantum mechanics. And so this is why I say that quantum is the theory of chemistry, of everything. And so quantum is the theory that we try to use to describe chemistry, right? And so we have the first shell, or the first period, the second shell, or second period. So the first shell is just 1s, second shell is 2s2p, third shell 3s3p, fourth shell is 4s, 3d, 4p. Right, and so we know the filling. Fifth shell is going to be what? 5s, 4d, and 5p. Sixth shell is going to be what?
6s, 4f, 5d, 6d.
Yeah, good. Good. Then we're going to go to chapter 9 next. Chapter 9 is a continuation of chapter 8. We're looking. There's you see these little peaks here?
Yeah.
Those peaks are signals from the atoms. These are 48 iron atoms that they manipulated to form this circle. And then these, do you see these spheres here? Those are copper atoms there. And so with a scanning tunneling microscope, you can image single atoms. Although these iron atoms look weird, it's because of the way the probe works. It measures potential. Here on the surface, it's a little cleaner. You can see the spherical shape of the atoms. And so there's a lot of proof now that atoms exist. Back in Dalton's time, there wasn't a lot of proof because did Dalton have a scanning tunneling microscope?
No.
No, but if he did, then everybody would have believed him. Do you think everybody believed Dalton?
Immediately, no.
So when we arrange things in the periodic table, we'll see different periods. So here, this is atomic volume. Atomic volume or molar volume, a mole of atoms has what volume here. And so we see this. Do you see this periodic pattern here? What elements have the highest atomic volume? Well, atoms have the highest atomic volume are the lower left. Yeah, like lower left. Actually, all on the left side of the periodic table, we have bigger volumes. And then what happens is we go to the right side of the periodic table. As we go to the right side of the periodic table, the volume gets smaller. But there's some kind of weird blips here. The volume gets smaller and then goes up again. And then goes back here. And so where's the minimum of atomic volume? So this is lithium and then beryllium and then boron. So boron's at the bottom here. And then this is sodium, magnesium, and aluminum down here. Potassium, calcium. And so we see this dip here, and then it goes back up here. And so we want to understand some of these. These are called periodic patterns or periodic trends here. And so we're looking at that. This is Mendeleev. This is an early version of the periodic table. But Mendeleev just based it on properties. Arranging things in organized fashion. That is, members of a family have similar properties, that is a column, and members in a period gradually change properties from metallic to non-metallic. Moseley, what did Moseley do? Yeah, unfortunately he died. Moseley was able to correlate X-ray frequencies to numbers equal to nuclear charges and corresponding to the positions of elements in Mendeleev's table. So Moseley, for example, aluminum, the 13th element, was assigned atomic number 13. And so Moseley was pretty critical in coming up with atomic numbers, and then atomic numbers were used to rearrange tables. But X-ray emission also is important because X-ray emission, you get a spectrum of emitted electrons, and so you can see the shells. So, for example, if you look at the emission spectra of certain elements, and usually it depends on where you go, higher energy to lower energy, and it's quantitative. So, for example, if we have energy going this way, or we could flip it and have energy going the other way, then these could be the S electrons, or the P, actually the P electrons be knocked off first. So we might have P electrons here, then S electrons here, etc. And so that's further evidence for organization of the periodic table, the way it was organized. But we don't really worry too much about the history of this. What we're looking at are the properties of this. So,
do we need to know Moseley's equation?
No, you don't need to know Moseley's equation. This is why as a student, I would never want to miss class. I'd never want to miss class because, do I need to know that equation or don't I need to know that equation? If I missed all the classes, then I'd have to memorize all the equations and all the material. There were a lot of equations. Do you have to solve the what do they call that?
You have to solve for the wavelength and hydrogen to find out.
You know, how important is it that did anybody do it? Did anybody graph a p orbital using Cartesian coordinates or polar coordinates or however you did that in the homework? You know, how important, if this were like say, if this were, like say UCLA and you have 4 questions on the test, then that could be a 25 pointer right there. And you'd worry about it. You'd worry that you know how to plot out a p orbital, maybe a d orbital, that kind of stuff. But, you know, if the instructor doesn't think it's that important, so they didn't spend any time talking about it, then maybe you don't need to know that. And so that would be less risky. Depends, you know. Sometimes the instructors will throw out some curveball, but most of the time not. And so, yeah, you want to know certain things. So the history is not that important. You don't need to know most of these equations. In fact, for chapter 8, what equations do you need to know? No, for chapter 8, I'll give you all the equations and all the constants. So you don't know. You need to know where to apply them. For chapter 7, I'll give you the basic ones. You know, Q is equal to mc delta T, Q is equal to amount times delta H, Q is equal to amount times delta U, work is equal to this. I'd probably give you the conversion from liters atmosphere to joules, even though you could derive it pretty easily. Yeah, 101.3.
101.3.
Yeah, kind of, right. 1.01325. Yeah. Exactly same. So it's not that hard to remember.
Do we need the Schrodinger's equation?
No, you don't need to know Schrodinger's equation. I mean, you've seen it. I'll show you the Schrodinger equation that I memorized. The Schrodinger equation I memorized is h bar psi is equal to e psi. So this h with a hat on it. This is called this is just algebra basically, and h is just an abbreviation for what they call a Hamiltonian operator. Hamiltonian operator is a bunch of mathematical things you put in front of this. It's a little bit different. You know, that's Planck's with h bar versus no h bar there. This is a little different. The sides are the same. They don't cancel out because we need to know. In other words, you operate on psi and you get the energy times the psi that comes out again. You don't want to cancel these out. If you cancel these out, then there's no operator to operate. And this is called operator. I forgot what this is called. Operator algebra. And so the psi's have to stay in there. You can't cancel them out. Otherwise, the operation doesn't work.
All right, because if you cancel out the size, operator equals energy, and then you wouldn't know what size.
Yeah, and you can't calculate. You have to do an operation on psi to get the energy. And this spits out psi again. It's weird, but you cover that. It's not hard. You cover it in differential equations. When you get to differential equations in linear algebra. No, not in Chem 1B.
No, it's calculus.
Yeah, it's calculus. All right, so what we're going to do is we're going to look at some of these trends. And so let's take a look at periodic trends in chapter 9. Probably one of the most important ones is size. And so when we look at the periodic table, which is the biggest atom on the periodic table? Lithium's not the biggest. Lithium's actually quite small. Yeah, lithium's small size makes it lithium's small size makes it a little bit of a misfit because what's this most powerful reducing agent on the chart, redox chart? Lithium. But it turns out lithium is not the easiest to oxidize. You know what the easiest element to oxidize on that list is? To take an electron from.
Fluoride.
Right.
Not chloride.
Fluoride.
Lithium is easy, but not the easiest. You know what's easier than lithium?
Hydrogen.
Probably the easiest one to oxidize is rubidium. You know why rubidium is the easiest to oxidize? Because it's bigger. How many shells is that? First shell, second shell, third shell, fourth, fifth shell. Fifth shell. So you're oxidizing fifth shell electron. It's way out there. Easy to take. It's easier to take. So rubidium is easiest to take. The problem is it makes a big cation. Rubidium plus is a big cation. It doesn't fit so nicely with water molecules. It's kind of big, takes up a lot of space, and the water molecules have to separate and make lots of room for the rubidium plus. The reason why lithium is at the top of the heap is because lithium ions fit nicely with water molecules. And so lithium ions love water molecules in that they form what are called hydration or solvation spheres that are quite stable. And so even though lithium is harder to oxidize, the product is nicely stabilized by water molecules. And so lithium is out of place. We wouldn't expect it. If there was no water molecule, then lithium would not be at the top. Rubidium would be at the top of this chart. And even better than rubidium is what? Cesium. Yeah. Francium would be the best. But since francium is radioactive and doesn't last very long, then we'll talk cesium. So cesium is the best. The biggest atom would be francium. But since it's radioactive, it's going to decay. Radioactive atoms have unstable nuclei that decompose. And so the biggest atom is at the bottom left, which would be cesium or francium. And the smallest atom would be
On the top right.
on the top right. And so this is the size trend here. Helium would be the smallest. Right? Helium's the smallest, francium or cesium is the biggest. Okay, then it goes smaller, like smaller than, let's say, francium, cesium, and then what? Rubidium, and then potassium, sodium, lithium, hydrogen. Is hydrogen bigger than helium or smaller than helium? Bigger. Okay, then we have below helium we have neon. Neon's bigger than helium, but is it? My sizes aren't. Is it smaller or bigger than?
It's smaller.
Lithium. It's smaller. And so the size trend goes like this. As we go left to right in the periodic table, the size decreases. And as we go up in the periodic table, the size decreases. Let's do this double arrow. Try to be more consistent.
If we were to find an element that's one under francium, would that become the biggest element, if possible?
Yeah. Right.
It would definitely be more radioactive.
Right. So if somebody were able to synthesize these and come up with element number whatever, then it would be bigger. Yeah, because it'd be another shell. And so the reason why, if we look, the reason why it gets bigger this way is because we're adding another shell of electrons. The reason it gets smaller going up is because we're removing a shell. And so the size decreases because we're removing shells. And so that kind of makes sense here, I think, right? Yeah. The thing about this is this. If we go to hydrogen, and then we go to lithium, and then we go to sodium. We take a look at hydrogen. Hydrogen is +1 with an electron. What's Z for hydrogen? Okay, that's H. Then we go to lithium. Lithium has 3 protons in the nucleus. How many inner shell 1s electrons does it have? 2. It has 2 1s electrons. Are 1s electrons good at shielding the 2s electron?
Yeah.
Yes. In fact, the inner shell electrons are highly effective shielders, so they pretty much cancel out the charge. So Z is equal to 3. Z effective is equal to about what?
1.
About 1. Because for every inner shell electron, one proton, and so we're only left with about 1 proton. And so that's Z effective. So Z effective is 1. Let's go to sodium. Sodium has how many protons?
11.
11 protons in the nucleus. And how many 1s? 2. And how many 2s? 2. And how many 2p's? And all those would be inner shell electrons, correct?
Yeah.
And then we look at the valence electron, and there's only 1 in the 3s. And so here we have 10 electrons core. Core electrons shield 100%. So even though Z is 11, Z effective is what? 1. Yeah, Z is equal to 11, Z effective is about 1.
But this amount increases as you go down, right?
Yeah. Because the bigger the orbital becomes, like for example, 1s versus 2s, what's better at shielding? 1s. But the bigger the orbital becomes, the more diffuse the charge is. So if we're looking at the shielding, let's say, of a 3s electron versus a 1s, then 1s is concentrated on the nucleus versus 3s is going to be more spread out. And so we can see this here. In fact, let's take a look at shielding in more detail. So we're going to spend some time looking at. They call the shielding or screening, whatever you want to use for this. They're synonymous. So we're looking at screening, shielding, and penetration. This one. I've just always called it shielding. And so let's take a look at shielding and penetration. This figure is not related to this. This is atomic size, which we'll come back to that. And these are the radial distribution functions, the RDFs. So you can see the 1s are very effective shielding. Also, the 1s are quite penetrating here. If you look at the 2s are the, which one is the 2s?
The black one.
The blue?
Yeah, the green is 2p.
The green is 2p. Okay. Yeah. The green is 2p, the blue is 2s. Which one's more penetrating? The green or the blue?
The green.
Oh, no, sir.
Are you sure?
2s is more
The better.
Because if we go right next to the nucleus, do you see this?
Yeah.
And the 2s orbital is weird because it has an inner sphere and then a concentric outer sphere. And so here we're looking at the outer sphere here, but there's a much higher probability that the electron's going to be close right next to the nucleus versus a 2p. The 2p is going to be the dumbbell, and this is half the dumbbell here. The other half of the dumbbell is over here. And so we have this inner sphere here, which is going to be symmetric, so we're going to see the mirror image of this.
So the penetration is relative to
How
where
close?
it is left and right? Not like,
You're looking at which one has a greater probability of being right next to the nucleus, and it's going to be the blue. Look how much higher the probability is. So if you pick right at the nucleus, the blue has this much probability, the green has 0, near 0 probability. And so looking out here, now overall it looks like the green is better because if you look at the mass of the graph, it seems to be closer, but that doesn't matter. What we're looking at is penetration. That is, the electron is not here all the time. The electron can sneak in. And so if we have an electron that's out here, it can sneak in much closer to the nucleus than this one can. And so that's what we're looking at in terms of penetration. Here we can see 3p are the 3p versus the 3s. Which one's more penetrating, 3s or the 3p? 3s, because it's right next to the nucleus. The 3d are way out here. So those aren't very penetrating now.
What are those dashed lines represent?
That's a good question. The dashed line represents
The dashed lines indicate distances of
the distance. They only mark two distances here. 0.5. This is going to be this is for aluminum. So this is just trying to give us some size perspective of this. So 0.5. So right. So if you're an electron in 0.5 angstroms, let's say the most probable distance for the 2p is here. Then what's going to happen is it's going to be shielded a little bit by the 2s. Is it going to be 100% shielded by the 2s? No. So this is what we call same shell shielding. Same shell shielding is not very effective, but there is going to be some shielding because that 2s can sneak in there and block. And if the 2s is here, then it's got 100% probability it's there and it's blocking the charge. But then it moves out here, then it's not blocking at all. And so we have to do this over time. Now, how about the 1s? Are those going to be shielding? Yeah, 100%. These ones are going to be shielding 100% if the electron's here. You know, if the electron were out here, then yeah, both the 1s and 2s, these would be the inner electrons would be shielding quite well. But I don't know why they picked 2 angstroms out, or 2 multiples. This is 2 multiples of the first. You don't have to worry about the distances. Oh, here it's 26 picometers is what they have.
They chose 2 angstroms because it represents n equals 2.
Well, this is 2 times 26 would be 52 picometers. This will be 52 picometers out. These are very small orbitals. This is aluminum. So here's the shielding here. This is for core electrons. Core electrons are going to shield 100%. So if you're a valence electron, you're not going to see the full charge. And so Z effective is Z minus the shielding or screening. Now, there's some rules for the screening here. To gain an appreciation of the possible magnitude of the shielding, the screening S, consider again the aluminum. And then they write the ground state. So these are all the inner electrons here. And they're going to, if we assume the inner core electrons screen the nuclear charge, shield the nuclear charge perfectly, and that the outer 3s and 3p electrons do not screen each other, then the 3s and 3p electrons would each experience a nuclear charge of 13 minus 10 core electrons, gives us plus 3. However, neither assumption is correct. That is full screening or no screening by outer shell electrons. And so this is overly simplified. This is what was seen in the MCAT exam there, which is kind of interesting because why do they care so much? So what we can do is we have a better model of this. Realistic values of Z effective can be obtained from analysis of wave functions. We can, in other words, we can do quantum mechanics. So if you want to do quantum mechanics, but calculating quantum mechanics are very difficult. Solving the Schrödinger equation is not easy. So it's quite difficult. And so what we have is we have something more qualitative versus something that's more quantitative. And so if we look at all the patterns, we come up with some numbers here. And so from the quantum mechanics, we see that valence electrons, that is, the same shell electrons, are about 33% effective in screening, etc. And so these are the Z effectives that they get. From this data, we can come up with some simple rules. Okay, simple rules to help us calculate. These are quantum mechanical values here. Let's see. And so the values in blue are for the ns electrons, the values in black are for the np electrons, if we have both s and p electrons in the outer shell. And if we have p electrons, then the s are supposed to shield a little bit. And so what we're going to do is we're going to take a look at Slater's rule, and we'll do a simple calculation of Slater's rule. Here, you don't have to memorize this equation or really do much with it. It just shows estimation of shielding, and where so let's do that really quick here. Actually, are we?
Yeah.
We have 5 minutes. Godspeed, Professor.
Well, 5 minutes is enough time to do Slater's. Slater's is pretty simple. What happened? I just had it. What number was that? 73? All right. 69. I don't like to do that. All right, 69. We have seen that wave functions of hydrogen-like atoms contain nuclear charges Z for hydrogen-like atoms and ions. We modified through equation 9.3 to account for the phenomenon of shielding or screening. In 1930, John C. Slater devised the following set of empirical rules. Empirical means what? From quantum mechanics? Observed. No. From observations to calculate shielding constant designated. Okay, so we write the electron configuration as such. And so these are same shell electrons. So 2s and 2p, same shell. 3s, 3p, same shell. 3d, etc., different shell. Electrons in groups to the right of the NSNP group contribute nothing to shielding constant. And so electrons that are farther out don't do anything. All electrons in the end, same, in other words, I have a simple set. Same shell electrons, 0.35.
No, 0.33.
33%.
Well, they said 33 there, but Slater has 0.35. All electrons in the n-1 shell shield 0.85. So if we're one shell in, let's say we're looking at 3s, 3p. If we're at the 2s and 2p aren't perfect shielders. They're only 85%.
Are we talking about principal shell or shell, like same n value?
No, yeah, it's gonna be the same n. It's gonna be the same n because of the size of the orbitals, and so it's not gonna be the same shell like a 4s, 3d, 4p. The spatial dimensions are going to be quite different. So the 3D are a lot closer in than the 4s and the 4p. And so the 3D are considered core or inner shell electrons. All electrons in n-2, so it is a principal, shield 100%. And so it's very simple. 35% same shell, first shell in, 85%, and then
Every other shell.
all the shells inside of that, 100% shielding. And so that's how much you deduct from it. And so we could do some simple calculations, but and then we're going to get those numbers, approximate numbers that we have there.
So it'd be like for hydrogen Z equals 1, and then lithium Z effective.
Yeah,
it'd
Z
be
effective.
1.1, say.
Yeah, so for lithium, we do, okay, this is one shell in, or one N in, and therefore going to be 85%. And so this is going to be a little higher than 1 because we're only going to shield 85% of plus 3. Yeah, something like that. And so that's what we'd end up here. For sodium, one shell in would be the two, so those would shield up 85%, and then two shells in or two ends in would be two electrons, and those shield 100%. So it would be 11 minus 2 minus 85% of 8, and then 35%. Well, there's no other electrons here, so we don't have to worry about that. That kind of thing is what you do. So this is just so you know, there are different levels of shielding, and we can do it in detail, but you don't need to know the details too much. Just